Okay, here's the final part of our video on the introduction to rotational inertia formulas. So we've already shown with a pretty trivial derivation where this formula comes from, and then we moved on to the formula for a rod when rotated about an axis perpendicular to the rod and passing through the center. Now, as the final piece, let's do a rod that's perpendicular to the axis, but instead of passing through the center, passes through the end. We start with our definition for rotational inertia, integral of r squared dm. We picture what dm looks like. So there's the rod, and instead of putting the axis through the center, let's move that axis over to the end point. The rod lies along our x-axis, and there's a dm, there's a dm, on and on we go. There's some random dm. That dm has a width of dx. Our very first dm is over here at x equals 0, and the final one sits at a position x equals L. So we make some substitutions. We say I equals the integral of, I guess by r. Right, here's the should we call that r, or should we call that x? Two ways of saying the same thing. So it's just as well to call it x squared dm. But remember, the ratio of dm to dx, if we find the density just of our element of mass, that's the same as the density of the entire rod. So dm is the same thing as m over L times dx. So in the next step of our derivation, m over L is treated as constant and comes out of the integral sign. We add our limits of integration, and this time instead of going from negative L over 2 to positive L over 2, we're going to go from 0 to L. And then we're left with the integral x squared dx, which comes out 1/3 x cubed. We have to evaluate from 0 to L. Evaluating for 0 is very simple. So what we really have in our final step is I equals m over L times 1/3 L cubed. Or in other words, I equals 1/3, let's see, the L and the L cubed cancel to give us L squared. Oh yeah, 1/3 m L squared. Let's just double check. Hey, look at that. 1/3 ml squared. In another video, we're going to see how we can go from 1/12 ml squared when rotated about its center to 1/3 ml squared when rotated about its end. In a different manner, we're going to use something called the parallel axis theorem. For now, just note that this axis rotation, although it's in a different location than the center, this axis of rotation lies parallel to this axis. And so I'll give you a preview for now, but save that for another video of how we can use the parallel axis theorem to derive the rotational inertia of a rod about its end as opposed to the rotational inertia of a rod about its center.